Hello everyone. Welcome to the MATLAB and Simulink robotics arena. My name is Maitreyee and we will today talk about how we can use ROS on a Raspberry Pi hardware using Simulink, showcasing an object tracking example. This is what we will cover today. We will talk about Simulink and how it can plug in with ROS. We'll see how we can deploy ROS nodes on Pi and then finally discuss the key takeaways. This is just a sneak peek into what we will learn by the end of the video. Here we see that we have a green colored object that is being tracked by the camera, which is mounted on top of a servo, which is in turn connected to the Raspberry Pi. And we see here that the messages that are sent from the Pi are received on the desktop. Now let's briefly talk about using ROS with Simulink. There are three ways of communication between ROS and Simulink. One is desktop prototyping. The second is using ROS bags. And the third is deploying standalone ROS nodes on the hardware. In this video, we would be focusing on the third workflow, which is creating standalone ROS nodes and deploying it to the hardware, which in our case is the Raspberry Pi. And for this, we would be using the ROS toolbox and Simulink support package for Raspberry Pi. So what we would have is a Simulink model where we would drag and drop blocks to create an algorithm. We will then generate C code from the model and directly deploy this particular model on the Raspberry Pi as a standalone ROS node with just a click of a button. For this, we would need a Raspberry Pi, a USB camera which is mounted on a servo, which is connected to ground VCC and GPIO pin 18 of the Raspberry Pi using connecting wires. Additionally, we would also need to install the Simulink support package for Raspberry Pi. Today, we'll showcase two different examples. In the first example, we will deploy ROS nodes which have vision and control algorithms on the Raspberry Pi, and we will validate these algorithms using another Simulink model which will be used for visualization. And the second one is built on top of the first one, where we are showing communication between distributed ROS nodes, one which is on the Raspberry Pi and the other one is on your desktop. Let's talk about the first example. What we do is first create a deployed executable vision and control algorithm on the Raspberry Pi to track a green colored object. We will publish the camera feed and the angle of the servo and visualize these results on our desktop. So basically we will have two models, one for our Raspberry Pi to generate a standalone ROS node and the other one on our desktop for visualization. Let's go to the MATLAB environment, and before we open our models, let's complete the setup task. The very first task for us will be to initialize the ROS master on our desktop using the ROS init command. If you download the repository whose link is provided in the description, you see that there are two folders. Let's open the first folder, which is called publish pi. Again, we see here that there are two different models. Let's open the model for Raspberry Pi. We have to now connect to a remote ROS device. We can do this by going to the robot tab in the Simulink tool strip and click on connect to robot. At this point, ensure that your Raspberry Pi is connected to the same network as your desktop. Fill in the IP address, the username and the password for Raspberry Pi to log in and click on test. And now we have completed our setup on a Raspberry Pi and it is now connected to our desktop. Now focusing on our model, we see that we have three separate areas which do three separate tasks. The first is obtaining sensor data, which is the camera data. The second part is the algorithm, and the third one is actuators and visualization of the data that is to be published from the Raspberry Pi. We get the input from the Raspberry Pi camera using this video capture block, where we have to set the device name where we are streaming the video from, the resolution of the image, and the pixel format along with the sample time. Here note that we have set the sample time in the Simulink callback, and to change the sample time you'll have to go to modeling, model settings, model properties, callbacks, and preload function, where we have set the sample time to 10 milliseconds. Coming back to the model, the R, the G, and the B channels are packed together as one and sent as an input image to the next subsystem, which is the image processing and controller algorithm. Let's open this subsystem. Here in the image processing section, we have used the MATLAB function and we have used blob detection to detect a blob of a color range which is specified here. And we output the centroid of the blob as X and Y. Let's go to the next block, Vision Results Processing Subsystem, where we draw circular markers at the centroid X and Y of the blob. And this is the image that is sent at the output. In the controller section, we have a tracking controller which is designed using state flow and has three states. First is when it tracks the object. Second is when it waits for the object to be in the frame. And third, if it does not find any object in the frame, where it keeps seeking to get the object in its frame. And here we calculate the necessary angle and this is sent as the output. Now we would need to package these outputs as ROS messages. Let's go inside the convert to slash camera ROS message block. And we see that we have used a ROS blank message, which is sensor messages slash image type from the various options that we have. And we replace the data according to our requirement in this MATLAB function. The output from here has the desired slash camera ROS message. However, for the server, we have used a standard UINT8 message as the template and replaced the data field with the servo angle using the bus assignment block. We now go and click on build and run to deploy this model on our Raspberry Pi. We see here that the camera is continuously seeking for the color that we have specified, which is green. And once we get a green colored object, it stops and tracks it as we move the object. Now let's run our desktop model for visualization. Here we are subscribing to the ROS messages which were published from the Raspberry Pi. From the received camera message, we are extracting the data and reshaping it to a M cross N cross 3 dimension message and then displaying on the video viewer. Similarly, we are displaying the data from the servo angle onto the display. Let's go to the simulation tab and run this model. And here we see that the video streaming from the camera and the servo angle updates in the visualization model, which is running on our desktop. Just like the last example, we would be publishing the servo angle and the camera stream from the Raspberry Pi. But along with this, we would also be subscribing to the color that is supposed to be detected on the Pi. This is the color that is published from our desktop model. To open the next model, open the Publish Subscribe Pi folder. Let's first open the desktop Publish Subscribe model. Here we see that the model is exactly the same as the last one, except for the addition of these two areas, which is publishing the minimum RGB threshold and the maximum RGB threshold. These are the range of RGB values that we would want our detected object to lie in. And to publish these values as ROS messages, we are using color RGBA standard message type. Similarly, in the Raspberry Pi model, we have an addition of this area which is subscribing to the minimum and maximum RGB threshold. We are using this threshold values in the image processing controller algorithm under blob detection in the MATLAB function. We are already connected to our Raspberry Pi since we connected it in the last example. Let's just test our connection and then deploy the model on the Raspberry Pi hardware. And once the model is deployed on the Raspberry Pi, let's run our visualization model on the desktop. Right now, the color which is specified using these constant values is green. Hence, it detects and tracks the green colored object. If we change these color thresholds to a value that is supposed to detect blue, we see that the Raspberry Pi tracks blue and not green. Similar to the way we have developed a Simulink model on the Raspberry Pi, we could manage a distributed system by deploying different models on different supported hardware and have them communicate over ROS. Coming to the key takeaways from this video, we learned how to connect a remote ROS device using the Simulink toolstrip. We learned how to automatically generate, transfer, build, and run ROS nodes from Simulink. And finally, we learned how to communicate messages to Raspberry Pi from our system and vice versa. That brings us to the end of the video. I hope you all have found this video useful for learning how to deploy ROS nodes on Raspberry Pi. Feel free to get in touch with us through our Facebook group or through roboticsarena@mathworks.com. Thank you.